Hi everyone, this is Sina, and today we're going to talk about the underlying mechanism of detonation, auto-ignition in spark ignition engines, especially the gasoline ones. So let's jump in right away. Before we dig into the subject, it is important to know some basic knowledge about combustion, normal combustion, and it is that, as you can see in this picture, this is the combustion chamber, this is the spark plug, and this is the piston. This A part is the already burned gas, and the U part is the unburned zone. And this thin layer, as you can see here, it is the flame front. Important thing is newly burned gases will expand behind the flame, resulting in more compression of the unburned gases, thus increasing their temperature. What does this mean? It means as the flame moves forward to the unburned zone, newly burned gases, because of the combustion, will expand behind the flame front and will compress the unburned gas in front of the flame and increases its temperature. Okay, in this picture, as you can see, uh, which was taken above the cylinder, uh, this is the burned zone, this is the flame front, and this is the unburned zone or the end gas. For knocking to happen or for detonation to happen or knocking or thermal explosion, anything like that, the prerequisite for that is that we have auto ignition in the end gas. So at some point in the burned gas, in the unburned gas, sorry, uh, there has to be auto ignition. And after that, it may develop into detonation or knock. Okay, in this slide, we need to talk about the multi-step nature of the overall reaction. As you all know, combustion is a chemical reaction. For example, if we have the gasoline here, it will react with oxygen and it will give us carbon dioxide and water vapor plus some released energy. But the overall reaction is not that simple. There are multiple steps involved at different temperatures, different pressures, different reactions will be activated, and previous reaction history will affect future reaction rates and activation also. For example, this is the simplified multi-step nature of combustion of alkane. As you can see, different steps are involved at different temperatures. At each temperature, different reactions are active, and they will create some chemical radicals. The nature of these chemical radicals and how they are being formed, with at which rate and with what kind of intensity, will affect future reactions activation and rate. So this is very important to know. The reaction is multi-step, and these reactions also happen at lower temperature. It means that even in the end gas, when the flame front is not uh, close, even at those temperatures like 600 degrees of Kelvin, we will have some low temperature reactions, will liberate some uh, chemical radicals. This is very important to know. Moving on to the next slide. So we have to define the auto ignition. Auto ignition has a pretty simple uh, definition. It is the rapid consumption of fuel and air which was not initiated by an energy input within or from outside of the system at the same spot. So this part is very important. At the end gas, if auto ignition happens, it will be a rapid combustion of fuel and air, and it was not initiated by an energy input, either from inside the cylinder or from outside the system. What does this mean? It means that, uh, for example, it was not initiated by another spark plug or another uh, spark arc, or it was not initiated by a hot surface, hot spot. That would be a different thing. So autoignition has to be on its own, and it will be a rapid consumption of fuel and air at that spot. So how it happens? It happens because there are some elementary and intermediate reactions that happened at some time before the autoignition. They kick in and prepare the state required for the rapid consumption of the fuel at the given spot. So what will happen after the autoignition? Depending on the end gas state, specifically temperature gradient around that spot, three different scenarios can happen. The first one being deflagration, the second one being thermal explosion, and third, developing detonation. So the deflagration is nothing very important. It will not develop uh, into detonation or knock at that spot. Deflagration is very similar to normal combustion. Like if we had a spark plug there, that would be a deflagration. After the deflagration, a normal combustion, a normal flame front will be developed and it will move on. But after the deflagration, at some point other than that spot which autoignition happened, we might get thermal explosion or developing detonation. But at that same spot, when deflagration happened, it will be a normal combustion. Thermal explosion and developing detonation will be the engine knock, but there's difference between thermal explosion and developing detonation, which we will cover in the next slides. Okay, in this slide, we're going to talk about factors affecting the autoignition itself. So we have different factors: time, temperature, fuel's chemical composition, mixture quality, and pressure. So what does the time tell us about autoignition? It tells us the residence time in any given state. So consider an arbitrary spot in the end gas. If it has enough time after, for example, some 4 milliseconds, 8 milliseconds, it will reach autoignition. So time tells us how much that spot has to reach autoignition. The temperature, it acts on reaction rates and active reactions. It tells us which reactions are active and at which rate they are active. Fuel's chemical composition also acts like temperature. It will affect reaction rates and active reactions. The mixture quality, by mixture quality I mean mixture strength, like how lean or rich it is at each spot. This also affects reaction rates and active reactions. And finally, we have pressure. Pressure acts on transport rate. The transport rate also affect the reaction rate. And also at different pressure levels, we have different reactions, so it will affect active reactions. Okay, so this picture demonstrates the mechanism of autoignition in the end gas. As you can see, there are four different sequences of combustion in these images. The first one being 2 degrees after top dead center, the second one 4, and then 7, and finally the fourth picture 9 degrees after top dead center. So the difference between first and fourth image is around 7 degrees of crank angle. As you can see, this is the flame front, this part here. After 2 degrees, it has advanced to this level. Before that, it was probably here, and in this picture, it's probably around here. The important thing you need to know is that green shows formaldehyde, which is a product of the intermediate reactions. The purple shows consumed formaldehyde or produced HCOH. So in the first image, in the end gas, which is this part, we have the formation of formaldehyde in the end gas due to low temperature elementary reactions. But as you can see, it's not homogeneous. meaning like we have formation here, but we don't have formation here. So at different spot, we have different rates of formation of formaldehyde. In the second picture, we have the same process, but this time more parts are developing formaldehyde. Uh, and in the third picture, we have seemingly homogeneous formaldehyde formation. Uh, but the important thing to know is that temperature is not homogeneous here. Like for example, probably the this part temperature is higher compared to this part. The reason is that when fuel and air are introduced into the cylinder, we will not have a complete homogeneous mixture at the end of the compression or during the combustion. Different spots will have different lambda values, like there will be some spots richer than other spot, or there will be some spot leaner than other spot. We will not have perfect homogeneity inside the cylinder. So because of that, we will have different reaction rates. The low temperature reactions will have different reaction rates because of the mixture strength, different mixture strength, and because of these elementary reactions happening at different rates, we will have different temperature values at different spots. So at some point, because of these elementary reactions and formation of formaldehyde, the temperature will go above a limit. And after that limit, high temperature reactions kick in and will consume remaining fuel and air at that location. And that will be the spot where autoignition happened. As you can see in the fourth picture, at this spot we had rapid consumption of fuel and air. And that will be our autoignition spot or exothermic center. So this was the underlying mechanism of autoignition. So after the autoignition happened in the end gas, as we said before, three different scenarios might happen depending on the temperature gradient and autoignition size at that location. So the first one being deflagration, as we said, it is nothing important. It will act just like normal combustion. So how should be the state around that autoignition spot for it to develop into deflagration? That autoignition spot shall be small, and around that spot there should be steep temperature gradients. And that will result into similar to regular flame front caused by a spark. No knock damage will be reported. The second one is thermal explosion. The autoignition spot shall be large, and around that autoignition spot, temperature gradient should be very small. This will result in low pressure oscillation and very moderate knock damage, if any at all, but it will develop into a very rapid combustion that will release a lot of energy at very small time intervals, which will result in some kind of shock waves, but not very strong shock waves. So it will develop some low pressure oscillation and very moderate knock damage. Most of the knock that you hear inside the engine is this kind of knock. It was resulted from a thermal explosion. The third and the most critical one will be detonation. The autoignition size shall be medium-sized, not too much, not too large, and not too small. And the temperature gradient around it shall be in a critical interval that supports the gradual growth of the pressure waves. So what does this mean, critical temperature gradient which supports the gradual growth of the pressure waves? It means around the autoignition spot, temperature levels should be in a way that after the moment that spot reached auto ignition, uh, and its combustion wave reached the other spot, that next spot also auto ignite. So these will add together like an avalanche and will create a huge pressure and combustion wave that will develop into a detonation like a phenomena. We will talk about that in the next slides also. Okay, in this slide, we have three different sets of image, in which the first one shows a normal combustion. The second one shows auto-ignition in the int gas, which resulted into a deflagration. And the third one, we have detonation. So in the first image, which is normal combustion after the spark event, we have the flame front after 4 milliseconds, which is advancing, and it's advancing and consuming all the unburned gases without resulting into a auto ignition or any knock. So during normal combustion, the flame speed is much more low, much fuck. So during normal combustion, the flame speed is much lower than sonic speed, and the pressure wave speed is also around the sonic speed. In the second picture, we had auto ignition, which resulted into deflagration. Just like the above image, we have the spark event. The flame front is developed after some 4 milliseconds and it's advancing. And at some time after that, which is around 8.2 milliseconds, we have auto ignition at the end gas, which was developed into a deflagration, which is still a normal combustion, no knocking. And in this scenario, also flame speed is much lower than sonic speed, and pressure wave speed is still around sonic level. In the third image, we have developing detonation. At first we had spark, and after some 4 milliseconds we had the flame front developing and advancing through the end gas. But at 8.3 milliseconds in the end gas, we had a auto ignition, which resulted into developing detonation, and the detonation wave is visible here. It's advancing. And as you can see, after just 1 hundredth of a millisecond, it has reached the end of the cylinder here. It's consuming the remaining fuel at much higher speed. So in this scenario, which is super knock and detonation, sorry, I have mistaken here. This is not deflagration, it's turned into detonation. So this is a super knock scenario. In this scenario, flame speed and pressure wave resulting from the combustion are equal and much higher than sonic speed. For example, the flame speed here is around probably 2,500 meters per second, but in these scenarios, flame speed probably is around 30 to 70 meters per second. Okay, in this picture we have the cylinder pressure. This is a detonation scenario. We have the cylinder pressure, and here we have time in milliseconds. As you can see here in this part, we had the pre-ignition. So this scenario is supernovae resulted from in-gas detonation initiated by a pre-ignition. So before the spark ignited, we had some pre-ignition event resulting probably from a hotspot or a flying hotspot inside the chamber. This results into a deflagration, a normal combustion event, but at this part, which probably after 2 milliseconds in the end gas, auto ignition happened, which resulted into detonation. This is the detonation wave, as you can see, and this part here we have the pressure sensor. So the pressure sensor is still reading normal values, But when that detonation front reaches this pressure sensor after some very small period, the sensor will read a huge amount of pressure value. As you can see here, this is where the detonation front has reached the sensor. And when this detonation front reaches the end of the cylinder, it will reflect back, as you can see here with this uh, red line here. Uh, it has reflected back and will go hit the other part of the cylinder and will reflect back again. And this will goes on forever. As you can see here, these oscillations here, this is what the pressure sensor is reading. So these oscillations are the results of these detonation waves hitting the cylinder walls and coming back again, reflecting back again. And after some period of time, uh, they will kind of fade away, but will result in this oscillatory behavior. Okay, so when knock happens, we have different knock levels with different intensity, and each one will result in different levels of damage or any at all. So in this picture, we have the cylinder pressure and crank angle. This is top dead center. This line is our compression line. The piston is moving up, compressing the air and fuel. And this, as you can see, this dashed line shows the normal combustion event. We had spark here, and after that the combustion started and pressure rise pretty normally, and the continuation of the power stroke. So this cycle 10730 is non-knock, but still probably some kind of auto ignition happened, which resulted in much higher cylinder pressure. But as you can see, it's not oscillatory, so it's not knock event. This line here is a slight knock phenomena. Again, auto ignition happened, probably some weak thermal explosions resulted into slight knock. As we go up, the intensity of the knock goes higher. We have heavy knock here with much higher oscillations, and these two scenarios are resulting from probably pre-ignition and resulting into detonation or super knock. As you can see, the cylinder pressure values are much higher with much higher oscillations. As you can see, the normal combustion maximum pressure is around probably 70 bar, but this one here goes all the way to 300 bars. And definitely this one is going to be much more damaging to the engine. So we have different knock intensities depending on the situation and depending on what happens after the auto ignition. If it's deflagration, pretty much it won't develop into a knock. But if it's thermal explosion, it will result into slight knock to heavy knock. And if it's a detonation, it will be there will be huge amount of damage to the cylinder. Also, the important thing is to know what amount of fuel is remaining when auto ignition happens. If the normal combustion flame consumed a lot of that end gas, there wouldn't be a lot of fuel remain to develop into detonation or thermal explosion. It means if it even developed into thermal explosion or detonation, because of the lower amount of fuel remaining, the damage will also be much more lower. But if the fuel remaining is a lot, definitely the damage will be even higher. So this was this first session in which we talked about the underlying mechanism of detonation and knock and also auto ignition. In the next sessions, we will talk about affecting variables and not, like, for example, what kind of effect has RPM and load and other parameters. The second one, we will talk about octane number and how relevant it is. Knock during acceleration will be covered, and how knock damages the engine. And also, at the end, we will talk about knock detection and mitigation in conventional engine management systems. Thank you all for being with me. Hope you like it. If you have any questions or comments, feel free to leave it. I will definitely answer you. Thank you all.